In this video, we are going to solve how to find a cycle in a linked list. Before that, let's see some examples and let's see what a cycle is. Let's take this example. In this example, the head is pointing to 3 and there are 3, 2, 0, 4 and the last element is pointing to null. This is the standard linked list. There is no cycle in this. For example, instead of null, if somebody is pointed last element to any of the previous elements, then this is a cycle. If you loop over this list, we'll start with 3 and we'll go one by one and we'll end at 4. In this case, we'll start with 3, 2, 0, 4 and again 2. The cycle continues. It will go till infinite loop. Now the task is to find whether such cycle is present or not. Let's see some examples. If you see in this example, there is a cycle. In this, there is a cycle where 2 is pointing to 1. In this, there is no cycle. It starts from 2, 0 and it's ending. If you see the last example, which is more important, in the empty list, there is no cycle. We have to handle such edge cases. Let's see the first method. How do you say whether a cycle is there? In other words, what we can say is, if we come across a node which is already visited, that means the cycle is there. What we can do is, we'll go one by one and we'll store all the nodes that are visited and we'll check the set. If it's already there, then there is a cycle. We'll use set to store because it gives O of n time complexity. There are alternatives to set in all the languages. Initially the set is empty. First we'll start with 3. It won't be present in set. We'll add it. We'll start with 2. It's not present. Move forward. 0 is not present. 4 is not present. Again we'll come to 2. 2 is present, which means cycle is there. So the algorithm can be written as go one by one, check in set, if present, cycle is there, add to set, add the current element to set. If we reach the end, no cycle. We have to go one by one till we find null. If there is a cycle, it will exit in this if condition. Otherwise, it will come to the end. So the time complexity is O of n, as we have to go through each and every element. Space complexity is O of n, as we have to store all the elements in a set. Let's write code for this. As we have seen in this first approach, we have to store the nodes in a set, and if it's already visited, we'll return that there is a cycle. Let's initialize the set. Here I'm going to write in Java, but the similar code can be written in any language. We need hash set to store the nodes. We'll start with the current pointer, which is at head, and we'll loop over this linked list. If the current pointer is present in the set, we'll return that there is a cycle because we have already seen it. Otherwise, we'll add the current set and we'll move to the next. Reaches the end, it means there is no cycle. Let's run and test this. You can see it's passing all the cases. In the previous method, the time complexity is O of n and the space complexity is also O of n because we have to store all the elements in some other set. Let's see a simple logic to eliminate the extra space. A time complexity we can't do anything because anyway we have to go almost all the elements to see if there is a cycle or not. The logic is we need some way to say whether we already visited that or not. While we go one by one, we can change the next pointer to the head. So what will become is, we'll change this next pointer of this to 3, we'll change the next pointer of this to head, this to head, and this also to head. How this helps is, when we go one by one, at the end after 4 we'll come to 2. The next of 2 is head. So in the entire loop, if you find head again, means somewhere it's already visited. Let me repeat again. You can change the next pointer to head so that in the entire loop will come to head again. That means it's already visited. Go one by one. Store next. If next is null, no cycle. If next is head, cycle, and change next to head and current to the whatever the previously stored next. At the end, if you reach, no cycle. I generally don't recommend this method because it involves modifying the existing linked list. You'll not be able to construct it again. You'll not be able to do any other operations once we do this. The time complexity of this is O of n, as you have to go almost n elements. The space complexity is O of 1, as we are not using any external space. Let's see the code for this. Here we need two temporary variables, current and next. The next can be empty initially. We loop over the linked list and we have to store the next before. If next is null, means we already reached the end. There is no cycle. If next is head, there is cycle. And change the current next to head and current to the previously stored next pointer. If we reach the end, there is no cycle. Even now all the cases are passing. Let's see the third method, which is the most optimal method. The intuition is, let's say you have a circle like this and somebody is running at a speed of 1 and there is another person who is running at the speed of 2. The idea is they'll meet somewhere on the path. They'll meet as one guy is running at a speed of 2, another guy is running at a speed of 1. So if they meet somewhere, that means there is cycle. The idea is we'll have slow pointer, fast pointer. Slow will move at a speed of 1, fast will move at a speed of 2, and in the loop, if fast equal to slow somewhere, cycle is there, or if we reach the end, no cycle. Let's see the pseudocode for this. We'll have slow, which starts with head. We have fast, which is also starts with head, and we'll check whether fast is not null. And the next of fast is also not null. Why? Because if there is no cycle, the fast or the next of fast might become null. We don't need to check for slow because fast will reach the null before slow. We'll change fast to 2 pointers. That's how it moves twice as fast. And slow 1 pointer. If they meet somewhere, if fast equal to slow, cycle is there. Otherwise, there is no cycle. And it is guaranteed that if there is a cycle, they both meet. The space complexity is O of 1, as we are not using any external space. The time complexity is O of n. It might seem that we have to loop multiple times until the fast and slow meet. But if you notice carefully, we might need 2, 3, or we'll see how many number of times we need for fast and slow to move in another video. But we can say that in some finite iterations, they both will meet. So even if it's O of 2n or O of 3n, the time complexity is O of n. The details of how many times we need for fast and slow to meet and where they'll meet, that we'll see in another video where we have to find the starting point of the cycle. That's another version of this question. Let's see code for this. This is one you have to use in your interviews. We'll initialize a slow pointer to head and fast to head. And while fast is not equal to null and fast dot next is not equal to null, we'll loop over this linked list. Why do we have to check both fast and fast dot next? Because at the end of the linked list, if there is no cycle, we may come to a case where one of this becomes null. If this is not null and this is null, in the code which we are going to write next, you may face null pointer exception or some issues because this can become null. We'll move fast to 2 pointers and slow 1 pointer. If they meet, there is a cycle. Otherwise, there is no cycle. As you can see, all the test cases are passing. This logic is very simple and you need to think in this way to solve harder problems. Thanks for watching. If you like this video, you'll like other videos on this channel. Please do subscribe for more DSA content. Do check the playlist on linked list where we'll solve almost all the problems. Thanks for watching and happy coding.